The extended Euclidean algorithm tells us that the greatest common divisor of two integers a and b can be written as the sum or difference of two multiples of a and b. So we can write d, the greatest common divisor, as a multiple of a plus a multiple of b. S and t will typically have different signs. In particular, if a and b are positive, then either s or t will be negative. So the sum becomes a difference, if you like. And moreover, we're going to give an algorithm for finding s and t. In particular, this theorem will be used for showing that prime factorizations are unique. The proof will be given by means of an example in the next slide. Before we do that, I'd just like to make one starred comment. The theorem asserts that there exist s and t such that the greatest common divisor is sa plus tb. But s and t are not unique. There are other integers which will work. And in fact, now this is a starred comment, for any integer k, positive or negative, if s and t are the integers that come to us from developing the extended Euclidean algorithm, as in the following example, which we will do, then I can add to s k times b over d. Remember, b over d will certainly be an integer because d is a divisor of b. And if t minus k times a over d will be then the multiple of b. And once again, this a over d is itself an integer because d is a divisor of a. Indeed, it's the greatest common divisor of a and b. It's easy to see, in fact, that this will work because all that I've done here, I've added on this side, this term here times a is k times ab over d, and this term is minus k times ab over d. So certainly this equality is true because we already know that d is equal to sa plus tb. And in fact, one can also prove that this gives you all possible coefficients of a and b. But in a sense that can also be made precise, the s and t, which you find from following the Euclidean algorithm, will be the smallest possible, or one of the two, in fact, smallest possible pairs. End of starred comment.